In this video, I am going to discuss long short-term memory, popularly known as LSTMs. I am assuming that you already know what are RNNs. So basically, in RNNs, at every time step, we have an input xt, and then we have a previous hidden state ht minus 1, and using that we generate the new hidden state ht. So these are the case for simple RNNs, but LSTMs have an additional state called as cell state. To solve the problem with RNNs, that is, RNNs do not capture sufficient amount of information for words that appeared long before in the sequence. If we are looking at the textual data, or in general, RNNs are not able to store long-term information. So cell state basically helps us to store long-term information of the sequence. And hidden state is same as like an RNN. Hidden state just stores the information about current cell, in this case LSTM cell, or we can call in RNNs we can call that as RNN cell. So hidden state is just a representation of the current cell. It stores that. It's more or less a short-term memory. So even if not current cell, maybe the problem with RNNs was that, like, beyond trigrams it does not perform very well, and that's why we need long-term information, and hidden state could only capture information from short-term, maybe trigrams or something. So we can say that current cell or maybe previous two cells, so it's basically captures some short-term information. So unlike RNNs, in LSTMs we have a cell state denoted by CT to capture long-term information, and we have a hidden state denoted by HT to capture short-term information. And now let's see that ultimately the variables of interest is HT. So basically the output YT is always dependent on HT. So if there is output YT, it's a function of it's dependent on some function of HT. Let's say f dash. But to but there should be a mechanism to capture the long-term information, so that if some of the output, let's say some YT, requires some long-term information earlier, then there should be a mechanism that YT can exploit that. So in other words, what I'm trying to say that this HT is nothing but a function of some function of, let's say, f1 of this long-term state CT. So basically some information of this long-term state CT would become part of HT, and we'll look into the details soon. And CT is updated based on what we already had stored in the long-term information. So previous long-term information, and how much new information we have to add and basically new information is provided by ht-1 and xt. So basically this generates the new information. Oh, sorry. So this is new information for cell state, because cell has not yet included ht-1 was derived from ct-1, and cell state ct has not included information from ht-1 and xt yet. So this is new information to be included in ct. So let's go into details of these outputs ht and ct, that how do we obtain this. So basically ct is determined by two things. So we already have some state ct-1, and ct is obtained by forgetting some of that. So let's say we generate a value ft between 0 and 1, and if you multiply this value with ct-1, it will tell us that how much of the previous long-term information we have to carry forward. So if it's ft is 0, that means we don't want to carry forward any of the long-term information we already have. If ft is 1, that means we want to carry forward all the long-term information we have till now. And then we generate new information, and so potential new information which we donate by c-t, and we see that, and then we also generate a number it again between 0 and 1, which tells us that how much of this potential information we want to carry forward as in our long-term state. So, and this c-t is the new information and will depend on xt and previous state ht-1. So this is the high level idea behind LSTMs. So let me formally describe what are these called. So this ft is known as forget gate, and this it is known as input gate. That is how much of the new input we are getting, how much of that do we need to carry forward in our long-term state. And this is our previous long-term state, and this is our candidate new information. Why I am saying candidate, because we are not passing all of it, we'll pass some of it depending on the input gate. So this is the candidate new information. So now let's see the details of this forget gate. So as I have already mentioned, that forget gate decides that how much of the previous state we need to carry forward, and forget gate is simply a neural network, one layer neural network whose inputs are previous state and xt. So in fact all the gates, forget gate, input gate, and we'll also talk about output gate later on, all of them have similar structure. So we pass the input xt and previous hidden state through one layer neural network, and then we applied a sigmoid function to get the values between 0 and 1. And similarly input gate is also generated using the same idea, and these neural networks for forget and input gates are different. In fact our candidate new state is generated by instead of using sigmoid activation, we used nh activation, and the inputs remain the same, ht-1 and xt. And if you remember, basically if we had a vanilla RNN, so this used to be our output for vanilla RNN. Basically, HT used to be simply some tan H function of HT minus 1 comma XT in our vanilla RNN, and there was no concept of cell state, but that's why we are calling it candidate. This is the candidate which we had produced as output if it was a vanilla RNN, but we are not producing this as output. This is still a candidate, and how much of this we would carry forward in the new cell state will depend on the input gate, as I already mentioned here. So if it was a vanilla RNN, we would just have outputted our candidate here to be as our next hidden state, but in this case we are not. And as I have discussed earlier, that our new cell state is nothing but simply, so forget gate times the previous cell state, and input gate means add some new values from the input times what was the candidate that we would had opted for if it was vanilla RNN, and this gives us basically our new cell state. So this is our new long-term cell state. And now, as I mentioned earlier, that some of this long-term information would be stored in our hidden state, that is short-term information, and that would again depend on, so basically we will again pass this long-term cell state through another tanh function. So in RNNs this is typical to pass, so the candidate, if it is a candidate or it's a final output, these guys are always pass through a tanh function. So output of an RNN or a recurrent neural network, whether it's LSTM or a GRU, would always be a tanh function or a multiplicand of tanh function. So new hidden state, which is kind of output, is basically the tanh of our new long-term state, but we don't do, so this is our, if we just keep this term, then this is basically we are keeping the complete long-term state. We are just scaling our long-term state using tanh function, but we don't want our complete long-term state to be our hidden state, so we want some of it. So some of our long-term state is our hidden state, and how much of it would depend on the current input. So this is again a value between 0 and 1, and this again depends on our current input xt and our previous hidden state ht minus 1, and then we pass it through a sigmoid function. So basically ht simply is some scale down information by a factor of ot, which lies between 0 and 1, of our long-term hidden state. So by maintaining CT, LSTMs helps to perform better, to capture long-term dependencies, and to basically help us get rid of the vanishing gradients or exploding gradients problem. To see that, we can observe that, let's say our ft is 1 and it is 0, then our next hidden state HT would be simply OT times tan H of CT, and since FT is 1 and IT is 0, CT is simply CT minus 1, and let's say OT is 1. So we can see that LSTM provides us a mechanism to simply carry forward our previous state, long term state CT minus 1, which is also our new state CT, without adding any new information to it. And this mechanism allows us to not multiply our input by a new weight again, and it helps in solving exploding gradient problem. For example, what I meant was, let's say CT minus 1 was some input x, and since CT is also x and ST is simply tan of x, we are not multiplying x with any more weights in this step. Otherwise, in vanilla RNN, you always multiplied the previous state x with some weight, and then in the next step you again multiply it with some weight, and in the next step you again multiply it with some weight, and this leads to exploding or diminishing gradients. But for LSTMs, we can avoid that based on the values of FT, IT, and OT. So I gave you an example where we are not multiplying it by weights. For example, here HT would be simply tan H of x, not multiplying it with weights. And then let's say again, if we choose it to continue like that, HT plus 1 would again be equals to tan H of x, because let's say CT remains to be x, then CT plus 1 also choose to remains to be x. And this is possible because if FT is 1, that we do not forget anything from the past, and IT is 0, we do not add anything from the new, then we keep on propagating the current long-term state without multiplying it with any more weight vectors w, and this kind of helps us to solve the vanishing or diminishing gradients problem. So I hope on a high level how LSTMs works are more clear to you. Now let's see how these gates changes for the case of gated recurrent units known as GRUs, which are more popular and my favorite because they are less complex. I think they work good in practice and they are not as complex, so I prefer GRUs. So here also we first find a candidate C dash T, and the only trick is that instead of finding the candidate based on the current input and the previous hidden state, the candidate depends on some of the previous hidden state. So reset gate is again a gate which gives the output 0 to 1, and it tells us that how much candidate should depend on the previous hidden state. And so the thing is, candidate depends on two things, xt and ht minus 1. So what GRUs are saying that definitely candidate should depend on xt because this is the new input, but it should not completely dependent on ht minus 1. So it should dependent on some of ht minus 1, and that is decided by reset gate, which Reset gate is again like all other gates that we discussed in LSTMs, is a function, is kind of a sigmoid applied on is a function of basically ht minus 1 and xt. So like other gates, or I used to write this simply as a function of ht minus 1 and xt. And instead of having two different forget gates and input gates, so the final hidden state is simply a weighted average of what's the previous hidden state. So we do not take the previous hidden state completely, so we forget some of it using this forget gate here. So 1 minus zt acts as forget gate, and zt acts as input gate, and zt is also again some sigmoid function of ht minus 1 and xt. And so this is our new candidate c dash t, and this is our previous output. So instead of simply taking c dash t, so if it had been a vanilla RNN, then our c dash t had been simply tan h of xt comma ht minus 1, right? So this was the case for vanilla RNN. So first we did what we did change, we didn't take the complete previous state, and then we just didn't take ht, the next state, to be simply the new candidate. We take some of the information from the previous hidden state. So we do not want to lose complete information from the previous hidden state. We do not want to completely discard the previous hidden state like in vanilla RNNs. So we want to keep some of it, but we also want to add new information that we obtain from c dash t. So basically they only have hidden state, they do not have a separate cell state. So the difference from vanilla RNN is that ht in vanilla RNN only dependent on the candidate obtained from ht minus 1 comma xt without taking some input of directly from ht minus 1, but here we are taking some input directly from ht minus 1 and some input using this candidate, and this candidate is also not just dependent on ht minus 1 but on rt into ht minus 1. So this is the difference between GRUs and RNNs. So I hope you like this video. If you like this video, please share it with your friends. Give a thumbs up, subscribe, and stay tuned as more and more good content is coming soon. Thank you for now. Bye bye.